Hello everybody. Today I'm going to present some of the work that I did in my fourth year project at the Higher Institute for Applied Sciences and Technology in Syria. We're going to talk about the development of an educational ball-on-plate platform that's presented by me, Ashraf Faraj, supervised by one of my professors, Dr. Michel Assala, Engineer Ali Abbas, and Engineer Noor Jawara. So the main goal of the project is to try to control the position of a ball on a plate. Now, this system, the ball on plate, is one of the most classical multi-input, multi-output systems that we use to test different control algorithms. So we're trying to connect a pre-existing platform designed in our control laboratory by two fifth-year mechatronics students. We're going to connect this platform with a MATLAB program through the Raspberry Pi microcomputer. The main goal is to try to replace the obsolete control and acquisition cards that we already have with a more flexible Raspberry Pi to allow students to test different control algorithms easily through the MATLAB program. So right here we see the main project block diagram. We see two main parts, the mechanical platform and the computing unit. So the mechanical platform, as we said, was already designed by two mechatronics students. It's actually a Stewart Goff 6 degrees of freedom platform, which means that we have six different motors. And right here, as we can see, we have six PWM signals that are issued by the Raspberry Pi to control these motors. Now, these motors control the orientation of the top platform on which the ball rests. The ball's position is sensed by a touchscreen, an ohmic touchscreen, which via the touchscreen controller sends the ball position to the Raspberry Pi. Of course, on the Raspberry Pi, we have a Wi-Fi connection with the MATLAB program, on which we have written our control algorithm. So at each runtime, we upload this program to the Raspberry Pi, which does the necessary computations, reads the pole position, and issues the appropriate control signals. So right here, we have a picture of the real platform and its main parts. As we can see, right here, we have the top platform. This is also the ohmic touchscreen. This right here is the ball. This is the platform. As you can see, we have six motors, 1, 2, 3, 4, 5, 6. These are the six fixed motors. All the motors are actually of servo type. And this right here would have to be the screen control. So this right here shows the main control block diagram of the whole system. At each time step, we're going to measure the ball's position using the touch screen. We're going to compare to reference to compute the error, which is fed to the controller block. The controller block then does the necessary computations to give control commands to the actuator subsystem, which in turn causes the upper plate to move in certain alpha and beta inclination angles accordingly. So as you can see, there are actually two main subsystems that we're quite interested in, which is the actuator subsystem and the ball-on-plate subsystem, both of which would affect our controller design. And we're going to discuss them next. So right here, we see the actuator's angular response. So as we said, the actuators are actually servo motors. So we'd expect them to have unity gain. So we were trying to command the actuator to move to, let's say, -5 degrees, as we're trying to do here. We expect that the actuator actually moves to -5 degrees with quite a fast response, sufficiently fast response, and unity gain. But actually, as we can see here, there's a little bit of static error, maybe in the order of 0.2 degrees, and the response time is about 20 to 30 milliseconds. Now, for the purposes of this project, we have completely ignored the dynamic effects of the actuators, and we have assumed that the actuator subsystem is actually one of unity gain only. Now, the ball-on-plate system can be modeled quite easily using Lagrangian physics. Okay, so it can be found that if we linearize the resulting nonlinear system, we could divide the whole motion into two independent subsystems, as the image shows, one describing the motion on the x-axis and one describing the motion on the y-axis. Now, both the differential equations describing this motion are given here, which are both double integration models. Okay, so that govern the relationship between the coordinates and the alpha and beta angles of the upper plate. Now, these constants, decays, are theoretically found to be 5g on 7, which is nearly like 7.01. Now here we're going to try to do a practical identification procedure of the system. And as we said, we have completely neglected the actuator dynamics and assumed they are only of unity gain. So we're going to go around this by actually closing the loop around the whole system, which is a double integrator as seen here. We're going to close the loop with only a proportional gain, K1, okay? So the closed loop system in this case would be expected to have an oscillatory response of fixed amplitude, because if we did the math, we're going to get a transfer function with a denominator of s squared plus a constant. In this case, we expect it to be a sinusoidal response signal. So we can actually deduce K right here, which is what we're actually interested in, by measuring the period or the frequency of the resulting oscillatory response, and then use the following relationships to compute the system's constants. This right here presents the positional response on the x-axis in a practical setting. If we used the period of the following response on the x-axis, we get a value of kx, which is 6.18. A similar experiment on the y-axis would give us a value of 6.83, both of which are quite close to the theoretical value. Not quite the same, as we can see, because we have actually neglected the actuator dynamics. Yeah, so now we're going to move on to the controller design. The first controller that we're going to talk about is the PID controller. First of all, we're going to write the system in state space form, which is x dot is equal to ax plus bu, x being the position and the derivative of the position. Now, from now on, we're going only to show the equations for one of the axes. The other one follows quite similarly. Now, the A and the B for this case are given as follows. The input is the alpha angle for the x-axis and the beta angle for the y-axis. We choose a control law of this form. That is, U is a matrix K multiplied by the vector of the tracking error and the derivative of the tracking error, plus a experimentally added integrator term. Now, this term has been used to try to eliminate the static error. The K has been computed to yield specific response requirements using the Boltzmann algorithm. This figure out here shows us the response on the x-axis using the previously mentioned BID control. We can see we have quite a good or satisfactory response of a response time of nearly 1.2 seconds, nearly no static error, a really small static error, and no overshoot. A similar response actually follows on the y-axis, having a response time of nearly 1.2 seconds, nearly no static error, and no overshoot whatsoever. This also shows the result of tracking a circular trajectory by the PID control, which you could see to have satisfactory results. So now we're going to move on to the second controller that we tried, which is the sliding mode controller. So the sliding mode controller is one of the robust nonlinear controllers that aim to eliminate the undesirable effects of disturbances and modeling error, which are usually unavoidable in a control problem. We're going to assume that our system can be written in the following affine form. The derivative, the nth derivative of x is equal to a nonlinear function fx of the state plus bx multiplied by u. We define a sliding surface S using the following equation, which is a linear combination of the error of the tracking error and its derivatives up to the order n-1. We're going to design the control law U in order to satisfy the following. It's made up of two parts, the U equivalent, which is a continuous part satisfying S dot is equal to 0, and a discontinuous part, U switching, given by the following relationship, KSW multiplied by the sine of S, to satisfy this condition right here called the reaching condition. Of course, further details about this can be found in the project report, which I'll provide in the description box. So one more practical consideration is that we don't design U switching the discontinuous control input as given in the previous slide using the highly discontinuous sine function. Designing U switching using the sine function might cause what we call the shadowing problem, which is exhibited in a high frequency control input, which might excite higher order dynamics, which were neglected in the preliminary modeling process. What we usually do is that we use a software approximation of Q switching given by the following relationship. K is W multiplied by the saturation function of S over phi. The saturation function approximates the sign function with a linear function in the region between -1 and 1. The phi is a positive constant that represents a trade-off between robustness and the soft control input. The final control law, by actually adding up the switching control input and the equivalent control input, is given by the following equation. This right here shows the response on the x-axis using the previous control input. We see quite a satisfactory response with a response time of nearly 1 to 2 seconds and a really small static error. Now, the same can be said about the y-axis, which exhibits also a fairly quick response of 1 to 2 seconds and a really small static error with no overshoot. This shows the results of tracking a circular trajectory using the sliding mode control. And finally, we have tested two sliding mode variants, okay, to try to solve some of the problems that we noticed previously. Nearly, as you can see, the responses as represented in the previous slides really exhibits some high frequency oscillations that we're trying to damp out using different types of sliding mode variants. So the first one is the proportional integral sliding mode controller. Now, I'm not going to go into detail of how we actually deduced this one right here. The details are available in the report. So what we did is that instead of the original surface, the sliding surface, we added a surface that has a component of the integral of the error. So we now have a sliding surface given by the following equation right here. As you can see, it contains the E dot, E, and the integral of the error. And we very much follow the same usual steps of the sliding mode control, in which we first compute the U equivalent, the continuous part of the control, and then add a switching part given by the saturation function. Now, the second variant that we tested was the superducing controller, which is part of a family of what we call higher order sliding mode variants. These try to not only drive the sliding surface towards zero, but also its derivative. Now, in this case, the control input is given by the following equation. The sliding surface is defined as the normal classical sliding surface. Now, this right here, we see the response of the proportional integral sliding mode control. We can see that the quality of the response has very much quite became better after using this type of sliding mode variant. We can see that we are quite faster. We are nearly up to maybe 1.5 seconds on the response time, nearly no static error at all. The same could be said about the Y coordinate response. It also exhibits a response time of 1.2, 1.3 seconds, and nearly no static. Now, this figure right here shows the trajectory tracking results of the proportional integral sliding mode controller, which exhibits higher accuracy than the usual sliding mode controller. Now we're going to show the results of the superducing controller. We can see that we right here have an extremely smooth kind of response, with no jacks or high frequency content in the response, and really, really small static error. The same can be said about the y-axis right here, which exhibits a really smooth response with a response time of nearly 1 second actually, and nearly no static error. Right here shows that the super twisting controller actually exhibits the highest accuracy on this trajectory tracking problem, where we can see that the trajectory is quite smooth and satisfies a really small tracking error. So this right here concludes the project, where in this project we designed and implemented an educational ball-on-plate system. As we said, we connected the pre-existing platform with the Raspberry Pi microcomputer, which in turn was connected to the MATLAB software on our personal computer. The main idea was to try to eliminate the obsolete acquisition cards and allow students to test different types of control algorithms. We designed and demonstrated the practical results for 4 different controllers to control the bolt position, either to a static position or through a circular trajectory tracking. And that's it. Thank you very much.